Discussion of the equations. Give you some examples of how we actually use them, what's easy to measure and what's difficult to measure. And then we'll turn you to some of the first, like, the real physics assignment today. So, I know, giddy with excitement. So here's where we're at right now. So we've got V equaling V naught plus AT, okay? Slope-intercept form. Your y-intercept, x is your time, you have your y-intercept, it's your slope, that's your acceleration, boom, there you go. Then you have one equation for distance, 1/2 v plus v naught time, okay? All that is basically saying, if you have accelerated motion, we're going to take the average of the two velocities, multiply that by the time, there's our distance traveled. Be careful with this one, because for some reason kids tend, even though this is written as plus, for some reason kids will tend to subtract these values, okay? And I don't know if because you're used to solving for acceleration, and acceleration is v minus v naught over time, okay? But if you're going to use this, and it's a handy equation to have, right? But just be aware that that's a plus and not a minus, okay? Because again, just think it through. It's like, oh, I'm finding the average of two velocities. How do I do that? I add the two numbers up together, I divide by 2, okay? And then the one that we came up with yesterday after we did all of those substitutions was 1/2 AT squared plus V naught time, okay? No. Oh, yeah, we still got to record.
Awkward,
So-
sorry.
It's okay. So, let's look at how we can use this in like an actual situation. So, Cooper, you might have to move so we can see this little bit right here. Okay. So, here's the deal. So, I've got the fan cart, right? And we can turn that on. And we'll let go of it. And it's going to begin to accelerate. So, what are some things that I could measure? I can measure time, right? I can measure how long it took to go between 2 points. Okay? What else could I measure?
How far it goes?
I can measure how far it went. Okay? I can measure distance. We'll make it simple. We're going to let it travel 1 meter. So we can measure how far it goes, and we can measure time. Now, do you think it's going to be easy to measure velocity? No. Okay? The velocity is going to be tough to measure because of the fact that we're accelerating. Oddly enough, therefore, our velocity is always changing. Okay? Now, if we had, like, if this was equipped with like a speedometer, and we could see how fast it's going at the end, okay, hey, that's something we could work with. But it's tough to measure velocity when it's continuously changing when you have accelerated motion. Okay? So, unless you happen to have a speedometer or like a radar gun where you can like, shoot it at it, oh, at this point it's going, 10 meters per second, whatever that is, okay? Now, if we're clever, and we are, what are we gonna let the initial velocity of the cart be? Zero, okay? So a lot of times what you'll see is that objects either start at rest and then they speed up, or they're moving and they slow down where the final velocity is going to be 0, okay? So, and I won't explicitly say, oh, the initial velocity is 0. What I'll say is, hey, a car, you okay?
I'm hot.
Okay. What I might say is the car is at rest and it accelerates at 5 meters per second squared or something like that. So that's what you kind of have to be able to read through the code, or is that, or the car is traveling and it hits the brakes and it comes to stop. Okay, oh, my final velocity is 0. So here's what I want to do. Cooper, I'm going to have you do a little timing, okay? So we're going to measure, just start and stop, boom, set, there you go, okay? So we're going to measure how long it takes for the cart to go from rest to travel 1 meter. So we're going to know distance, we're going to know time. What else do we know?
Initial velocity.
Initial velocity is going to be 0, okay? So I'm here, I'm going to let the fan get up to full speed, so that way I'm producing a uniform acceleration. So you ready? I'm going to go 3, 2, 1, go. Ready? 3, 2, 1, go. What'd you get?
3.65.
3.65 seconds. Okay. So here's what we got. You can move back over now. So we've got a time of, so here's our cart, okay? Boom, took off. And we measured the time to be 3.65 seconds. It traveled 1 meter. We know the initial velocity is 0. Okay? Now, I want to calculate the acceleration. Okay? That's what I want to find first, is the acceleration. So could I use, to find the acceleration, could I use that slope-intercept equation to find the acceleration?
Yes. Wait.
Yeah. Well, you have to find the velocity first.
Well, I know the initial velocity, right? So I got this number. I know the time. Got that. But do I know the final velocity?
No.
And I don't know the acceleration. So I'd have one equations with two
You
unknowns.
can use this
So you should use
the bottom.
the second one
Now,
to find the regular velocity.
could I do this to find the final velocity?
Yes.
I could, okay? I could do that, but it's gonna be a god-awful amount of work that I don't wanna do,
That one.
okay? Could I use this equation?
Yeah.
Yes, because what's my
yeah.
initial velocity? 0. So when parts of equations drop out, generally what you do is you draw an arrow like this and you put it, and then you put a 0. It says, okay, this part of the equation drops out. Okay, I don't have to worry about that. That was the advantage of letting the cart start at rest. Then I don't have to worry about that part of the equation. Okay? Now, again, so if I'm going to solve this problem, I'm trying to find my acceleration. So I'm going to distance equals 1/2 at squared plus v naught time. That's going to drop out. I don't have to worry about that. So I need to solve this equation for time. So what am I going to do?
Wait, I was like,
I need to solve for acceleration. Multiply by 2 and then divide by,
T squared.
and then I'm going to get a. Okay, don't take, the only thing that's squared here is time. I'm not squaring acceleration, okay? So when you solve for this, don't like put that underneath the radical. Now, at this point, now it becomes pretty simple. I've got it solved, I know what I'm looking for, and then I'm going to go, oh, that's 2 times 1 meter. I'm going to divide, and then somebody get out a calculator, and the time is 3.65 seconds squared. So what,
13.3.
what'd you get?
13.
Oh, there's no way. No, the whole thing.
Oh, the whole thing.
Yeah.
You just meant.
No,
Yeah.
the whole thing.
Okay.
You take 2 and divide it by 3.65 squared.
It's 0.150.
0.150? Okay? Now, to give you some perspective, when you drop something, that's an acceleration of 9.8 meters per second squared. So that acceleration going across was pretty slow. Now, that doesn't mean that I can't get that cart to go really fast. It would just take a long time, okay? So I had an acceleration, I had a change in velocity, it just wasn't a rapid rate of change in velocity. Now, I take this and I strap like a rocket motor on the end of it, and then light the rocket motor, whoo, okay? Oh, that's gonna accelerate really quickly, all right? So then what would happen is that we would be dividing by a smaller time. That's gonna increase that acceleration. Okay. Now, at this point, since we know the acceleration, could we find the final velocity? Yeah, okay. So now you could go, oh, v equals v naught plus at. What's my initial velocity? 0. I don't have to worry about that part of it, right? So I can take 0.150 meters per second squared, multiply that by, what was our time? 3.65 seconds. And what do you get?
5.48.
What?
5.48.
No, 0.15 times 3.65 does not get you that.
0.5.
Oh, point. Sorry, I read it wrong.
I was gonna say, whoa, something's wrong. What'd you get?
0.54.
Wow.
0.54
Right
Eight.
numbers, wrong decimal places.
meters per second. Okay? Seems reasonable. That's not all that fast. All right? Now, this is how you can use these equations. Okay? So now we took something simple. We just let this thing accelerate from rest. And this is a technique we're going to use a lot. Okay? To calculate acceleration. Because acceleration's tough to measure. Because you're trying to measure a rate function of a change in velocity. And even calculating the velocity is tough because that velocity is always changing. Now, to get the final velocity, could I take 1 meter and divide that by 3.65 seconds to get my velocity? No. Categorically no. Stop. Horrible. Why?
You need a constant velocity.
You need a constant velocity. Did the card have constant velocity? No. So if you try and find yourself using this, unless I explicitly tell you that it's constant velocity, don't. Okay? Don't use it. All right, so let's look at how this plays out mathematically. So let's say we've got a carrot car. Initial velocity is 0 meters per second. It's at rest. And it's going to accelerate at, say, I don't know, 4 meters per second squared. And I want to figure out at the end of 1 second, 2 seconds, 3 seconds, and 4 seconds. I want to know a couple of things. I want to know how fast it's going, and I want to know how far it's gone. And then I want to draw a position time graph and a velocity time graph. Okay? So here's our cart, right? It's going to start at rest. It's going to accelerate much faster than this one. That's going to accelerate like at 4 meters per second squared, right? And that's typically, like when you drive your car, if you kind of punch it a little bit, that's about when you're going to get an acceleration of about 4 meters per second squared. Like you really have to hit the gas to get something around 8 or 9 meters per second squared. Okay, so this is 4 meters per second squared is a fairly decent acceleration in your car. So I know acceleration and I know my times. Okay, so how can I figure out my velocities at those points?
An equation.
An equation.
Let's look which one.
But let's think this through.
We could do the first.
Is the car going to be speeding up?
Yeah.
Yeah, it's at rest. Can't go much slower. Okay, so the car's going to be speeding up. So even though we won't get there yet, what would the velocity time graph look like?
A positive.
A straight line.
Yeah.
Positive sloping line like this?
Yeah.
Yeah.
And what would the slope of that line be?
4, 6,
Acceleration.
Yep. 4 meters.
4 meters per second squared, which is the acceleration, right?
Right.
Okay? Yes?
Would would it reach a top speed ever?
Oh, it will. It would eventually.
Okay.
Okay, it'll, yeah, but we're not going to worry about that.
Okay.
It will eventually. That's even this cart. Like if I let this cart go long enough, it's not going to break the sound
Well,
barrier.
yeah, that's what I figured. I just didn't
Yeah.
know if we had to.
No, we're just going to look at it while it's still accelerating.
Okay.
Okay. So we know the slope of the line. So if you're a math nerd, you go, oh, I know the slope of the line. It's got a y-intercept of 0. Hey, I know my x values. I can find my y values. Now, this is where it's important to understand fundamentally what acceleration means. Okay? When you see that acceleration of 4 meters per second squared, what we're saying is that for every second that goes by, that velocity changes 4 meters per second. So if you start at 0, at the end of 1 second, how fast are you going?
4 meters per second.
I'm going 4 meters per second. Okay? That's what that number means, is that for every second that goes by, it increases 4 meters per second. So if you go another second, you're going to go up to 8. And then you're going to go to 12. And then you're going to go to
16.
16. Okay? So if you like a step-by-step process, oh, Mr. Burkamp, I love using slopes. That's cool. Good for you. Okay? You can think of it that way. Okay? And it makes sense. And conceptually, that's important that you understand what that means. Some people like a monetary analysis or analogy. Imagine that you show up to work and you have no money, but you're going to make $4 for every second that you work. Okay? That's sweet. Okay? So if you show up with no money, and you work for 1 second, how much money have you made? $4. Then you're going to be at 12, then you're going to be at 16. Okay? So if you like a monetary analysis, you can think of it, oh, that's the rate at which my bank account is going to change. Okay? Now you go, but oh, Mr. Burkamp, we have equations. Yes, we have equations. Let's look at the equations. So you can go, oh, okay. V equals, oh, come on. Why won't you write? Seriously. There you go. Okay? So if you're an equations kind of person, Mr. Burkamp, we have an equation. The beauty of this is that we don't need to solve it for anything. It's already solved for the velocity, which is just going to basically be your y values. So you have no y-intercept because the initial velocity is 0. Okay? So you don't start there. So you don't have to worry about that. So here's what's going to be important for those of you that like math. Notice that that's 4 meters per second squared times 1 second, and we're going to get 4 meters per second. And then we'd have plug in 2, and then we'd get 8. And we'd plug in 3, and we'd get 12. We'd plug in 4, and we'd get 16. Okay? So notice that, and this is one of the most important things, notice that velocity changes as a linear function of time. Okay? Because it's just acceleration times time. This is why velocity time graphs have a straight sloping line. Because when we talk about uniform acceleration, we're assuming that the velocity is changing the same amount in each time interval because we have the same amount of force applied over each time interval. Therefore, we have the same acceleration. Therefore, we have the same rate of change in velocity. So it's kind of like this big circle. Okay? So acceleration and time and velocity are a linear relationship. And if you go, man, how do I remember that? Look, this is just acceleration times time, okay? It's a linear function. It's a slope-intercept, okay? So velocity changes as a linear function of time, okay? Now, let's figure out now how far it went. And I'm going to give you a couple of options on this one, okay? So we need to figure out how far it went. So one option is you go, Mr. Burkamp, oh man, I love triangles. Okay. So we have this little triangle here, right? Because we know at the end of 1 second, we were going 4 meters per second. So if you like triangles, you can go, oh, I know the base is 1 second. I know the height is 4 meters per second. Area of a triangle, 1/2 base times height. So it's like, I was president of the area of the triangle club. Good for you. You can use this, and it's cool, okay? You can do this. If you want to do this, that's fine. There's a disadvantage to it, which we'll talk about later. But one option is that you go to your velocity time graph, and you go, at the end of 1 second, I'm going 4 meters per second. I take 1/2 of 1 second times 4 meters per second, and I'm going to get 2 meters. Okay? That's an option. Works. Okay? Works. Now, here's the disadvantage of this method. Okay, here's the disadvantage. If you found that final velocity of 4 meters per second, if that 4 meters per second value is wrong, this calculation is going to be wrong. Okay? So as you go through these problems, you want to try and work with known values as long as you can, okay? Because literally, if you've screwed up the 4 meters per second, you've screwed up the area. Then you screwed up the area, then you screwed up your displacement, okay? It works, but that's your trade-off. Now, why couldn't I just take 4 meters per second times 1 second and go, oh, it went 4 meters? That'd be the easiest thing to do. Why can't I just take 4 meters per second times 1 second and say it went 4 meters?
Did you start out at 4 meters per second?
Yeah. It's not going 4 meters per second the entire time. There's only one point in time where this thing is going 4 meters per second, and that's at exactly 1 second. It's going 2 meters per second. It's going 1.2 meters per second. It's going 3.14 meters per second, okay? It's going through this whole range of velocities. So that's why you just can't take 4 meters per second times 1 second and go, oh, it went 4 meters, okay? Now, the other thing that you could do, and this is what I would do. What I would do is I'd look at this and go, okay, hey, distance equals 1/2 AT squared plus V naught time, okay? The cool part about this one is your initial velocity is going to drop out because the car started to rust. I don't have to worry about that part of it. The other thing is that conceptually, now I'm going to look at this and go, wow, this is multiplied by t squared. So anytime you see something squared, you know it's going to be a quadratic function, okay? So here's the difference. If you look at v equaling v naught plus at, that's just acceleration times time. That's a linear function. This one, I have acceleration times time squared, which means it's going to be a quadratic function, okay? So whenever you see something squared, when you go to graph it, it's going to be a quadratic function. So in this situation, I'm going to take 1/2 times 4 meters per second squared times 1 second squared, and I'm going to get 2 meters, okay? Come on, okay? Okay? Now notice I get the same answer, okay? Which I should. I can't have the area of the triangle producing one answer and one of my kinematic equations go, no, it went a different distance, okay? They both have to produce the same one. The advantage of this one is that you're going off of known values. I'm not basing this off of that 4 meters per second, okay? So that's the advantage of using this one, is that you are going off of values that are in the problem, okay? So that's one advantage. Now, the next one, we need to go at 2 seconds. So that's for 8 meters. Now, I want you to notice one thing. Because this is time squared, and I doubled my time, I went from 1 second to 2 seconds. I doubled my time. But look what happened to the distance. How much did my distance increase? By a factor of 4, okay? That's the whole point of this thing being a quadratic. When it was acceleration time, and I doubled the time, I doubled my velocity. But when it's distance versus time, because it's time squared, if I double my time, it goes up by a factor of 4, okay? Because it's t squared. Now, at 3 seconds, the only thing you're changing is that value of time, 9, 36, 18 meters. And then you got 4 seconds, which is 16, 32, okay? Now, so now we're going to draw the position time graph, okay? So this is where this is all going to come together, hopefully into one big idea. So my position time graph is going to look something like this. So there's 1, 2, 3, 4. 4, 8, 12, 16, 18. So here's the deal. At 1 second, we had traveled 2 meters. At 2 seconds, we had traveled 8 meters. At 3 seconds, we had traveled 18 meters. So notice that this line is very much a quadratic curve, okay? Because again, what does the slope of a position time graph give you?
Position versus time.
Slope of a position time
Oh,
graph
velocity.
gives velocity, okay? What's happening to the velocity?
Speeding up.
It's increasing, therefore the slope has to get
Bigger.
bigger. Now, here's the culminating question out of all of these. Okay, I've been leading up to this one culminating question. I'm going to come out here at the 1 second mark, and I'm going to draw a tangent line. What should the slope of the tangent line be at exactly 1 second?
The 4.0
4.0 what?
meters per second.
Why? Your answer's right. Why?
Because that's a tangent line, so it gives you instantaneous velocity.
At the end of, and at the end of 1 second, you are moving at
4 meters per second.
4 meters per second. So if I come out here at 1 second and I draw that tangent line, it's going to have a slope of 4 meters per second. Now, if I go to 2 seconds and I draw that tangent line, guess what? The slope's going to be 8 meters per second. If I go to 3, the slope's going to be 12 meters per second. So as time goes by, these tangent lines are becoming more steep, which is why this thing becomes a quadratic function, okay? So that's where it all comes together, okay? So position time graphs, those slopes gives you an instantaneous velocity. You can find that instantaneous velocity by finding your velocity if you know the acceleration and the time. And then that gives you the slopes of the tangent lines. Got that?
Yes.
Okay. So here's, I want to emphasize this again. Position changes as a quadratic function of time, okay, because it's t squared. Velocity changes as a linear function of time because it's just acceleration times time. And I promise you, I'm going to ask you this question, okay? I promise you, it's going to be a multiple choice question. I'm going to say, velocity changes as a blank function of time, distance changes as a blank function of time. One's linear, the other one's quadratic. And if you don't remember which one is which, oh, look, that's acceleration times time. That's a linear function. Oh, that's acceleration times t squared. That's a quadratic function, okay? It's the easiest way to do it. All right. So, stand up, stop that, take a quick stretch. We got one more equation. So here's the last of the 4 equations. And this is the only one that kind of has its own name. And this is the one that, and this started many, many years ago. It's just known as that equation, okay? So if you say, hey, let's use that equation, everybody knows which one we're talking about. So here's the difference. So if you look at that equation, v squared equals v naught squared plus 2ad. What's missing from this equation that's in the other 3?
Time.
Okay? So if you ever have an equation or a problem, I should say a problem that doesn't involve time, and you're flipping out going, oh, I don't know what to do, that's where that equation comes in, okay? So if you get problems that do not have time, don't flip out and go, oh, I don't know what to do, okay? Now, you'll eventually derive this equation. It comes from the idea of conservation of, why did you put the pencil in?
For fun.
This comes from the conservation of potential and kinetic energy. Like when you drop something, it begins to fall, you have potential and kinetic energy. So on one of the last assignments that you do, you'll derive the existence of that equation. For now, just accept it, okay? So here's how this one would play out. You would say, okay, here's the carrot car, and let's say that it's moving at, I don't know, 5 meters per second, and it's gonna speed up to 20 meters per second. And we know most cars accelerate at 3.5 meters per second squared. I wanna know how far this is gonna travel, okay? So again, I'm an engineer, I'm building a road. I know cars are gonna go from 5 meters per second to 20 meters per second. On average, they're gonna accelerate at about 3.5 meters per second squared. I wanna know how long do I need to build this road, okay? And again, here's what I don't want you to do. I don't want you to read this and flip out and go, oh, I have to find time, okay? You can't. There is no way to find time with the information that you have, okay? You don't, because you don't know time and you don't know distance. So when you get a problem like this is the beauty of that equation. So when you read a problem and you don't have time, don't flip out and go, oh, this is bad, okay? This is why that equation exists. So, if you want to do the variables, we've got V naught, data, okay? Time, not there. I'm not asked to find time, I'm not given time, I got nothing. This has nothing to do with time. I know my final velocity is going to be 20 meters per second. My initial velocity is 5 meters per second. Distance traveled is what I don't know, and I know my acceleration is 3.5 meters per second squared. Okay? So now I know what my variables are. I don't have time. I'm going to go to that equation plus 2AD, right? Cool with that. Now, I need to solve that equation for distance. Solve these equations, okay? So if you solve that equation for distance, what are you going to get?
B squared
B squared minus
minus B naught squared.
B naught squared divided by
2A.
2A. That's it. There's my distance. Now, here's the deal. Do you think your displacement's going to be a positive or negative number?
Positive.
Positive, right? On this velocity, if you were to draw a velocity time graph, you're going from one positive velocity to a bigger positive velocity, and that area is going to be a positive number, okay? You know your displacement's going to be positive. If you do this and you get negative displacement, whoa, something's wrong. So you're going to tell me I have a car moving forward in a positive direction, and it's speeding up, but yet I'm going to have negative displacement, which doesn't make any sense at all, okay? So, in this situation, my final velocity was, what, 20 meters per second? Minus 5 meters per second, divided by 2 times, what do you say, 3.5 meters per second squared. Okay, so somebody run the numbers. Now, here's a cautionary tale. Don't take 20 minus 5 and then square it, okay? You have to square them separately, subtract, and then divide. Now, when you do this division, be careful how you input that on your calculator. Don't take this and then put, divide by 2 and then times 3.5. If you're going to do that, you have to put that in brackets, or otherwise, because if you put divide by 2 times 3.5, it will literally divide it by 2, get an answer, and then it will multiply that whole thing by 3.5. And that's a huge difference as compared to dividing by 7, okay? So if you're going to do this in steps, and when you're doing these problems, I don't need to see what you get out of this. You don't need to write down, that's 400 minus 25 divided by 7. I don't need to see that, okay? I don't. If you really want to write that down, you can, but I don't need to see what you get out of those sub-calculations. I need to see this, I need to see this, okay? But I don't need to see your sub-calculation numbers, okay? Anyway, so what do you get?
53.6 meters.
53.6 meters. So that's about half the length of the football field. Okay? Got it. Good? Now, I can work these problems all day long. Until you all begin to work them, that's when you're gonna get a real feel for it. So, stop that.
Because you're so
So, here's when you get assignments like this, okay? You're gonna treat this as basically like a page out of a textbook. Nothing gets answered on here, okay? Nothing. So even on that multiple choice, don't answer here. You can write on this, you can make notes, whatever. But I'm not grading anything that is answered on this green sheet, okay? Not gonna do it. So what I'm gonna do is, so on these multiple choice, you're gonna answer those on another sheet of paper. And on the back side, I have shown you exactly the format that I want these done. So I'm gonna make sure everybody's cool. So on these, you're gonna start off, and here's your piece of paper, okay? And you're gonna come over here and you're gonna draw a line. Maybe an inch and a half, something like that, okay? So the only thing that's gonna go here is going to be your answers, and over here is gonna be the work that's gonna generate those answers, okay? Now, the reason I have you do that is because I found that this is the easiest way for me to grade things, okay? That way, I can go down this column, I can check the answers, and then I can look over here, and then I can check the work that generates those answers, okay? When you're trying to figure out how to lay this out, don't view it from your perspective, view it from my perspective in terms of when I have to grade these papers, okay? Like, there's 26 of you in this class, okay? So, that takes me a while to grade 26 papers. So you want to make this as simple as you can. This is why I don't want you to like randomly write down stuff and then all of a sudden you box an answer and then I've got to go through and try and find that answer, okay? That's a waste of my time, and love you all to death, but I have better things to do with my time, okay? I grade all your papers, I spend a lot of time doing it. This is the most efficient way to do this. So, you're going to answer 1 through 6. 1, 2, 3, 4, 5, 6, boom, okay? There you go. Most multiple choice don't require calculations, okay? It's just conceptual kind of things. If you do have to do some calculations, you can put those off to the right. Now, the heart and soul is when you get to like question number 7. Now, 7 is a situation where you have to write out an explanation. It doesn't happen very often, but generally, most of the time, I'm going to make you write something. So when you answer number 7, you can go across the border, okay? So you're going to say, yes, this, whatever, blah, 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 okay? So when you're answering a question, you can cross the border between the answer line and the work line, okay? Now, let's talk about number 8. So I'm going to work number 8. I'm going to show you exactly how I want number 8 done. So here's your sheet of paper, okay? And you've answered your multiple choice. You've answered number 7, da 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 da. Now you're ready for number 8. Here's this line, okay? So, and again, you don't have to write down the variables, but if you want to, you could come over here and go V naught, dat, okay? So if you look on number 8, the rocket lifts off its launch pad. So what do you think the initial velocity of the rocket is? 0, okay? All right, so my initial velocity is going to be 0. You're told that it's going 100 meters per second, which is about 1/3 the speed of sound. Okay, so now I know my final velocity. And that's going to take 10 seconds. And I'm not told anything about distance, so I don't care about that. And I'm searching for my acceleration. Okay, so at this point, think this through. And again, every acceleration problem can only be one of 2 things. I'm either speeding something up or I'm slowing it down. That's it. Now, I'm going to start with this rocket at rest, and it's going to end up with a positive velocity. So what's going to be the sign of my acceleration? Positive. So if I know I get a negative acceleration, I've done something horribly wrong, okay? So literally, start each problem with that thought. Am I speeding up? Am I slowing down? If I'm speeding up, make your velocity and acceleration have the same sign. If they are opposite signs, or if they're opposites, you're going to slow down. So what I would do is I'm going to sit here and go, okay, I know V equals V naught plus AT. That's the equation that I'm going to start with. The beauty of this is that there's only 4 equations, okay? Literally, the test next Tuesday, there's only 4 equations. That's the only thing you have to choose from, okay? You got a 25% chance, even if you just randomly guess, which hopefully you won't. But now, I need to solve this for acceleration. So I'm going to have V minus V naught over time equals my acceleration. So then I'm going to have 100 meters per second minus 0 divided by 10 seconds, and I'm going to get 10 meters per second squared. So over here, I'm going to write 10 meters per second squared. Notice that I have 3 significant digits, okay? Every answer on all the numbers that I've given you at least 3 significant digits, okay? Now, I'm done with number 8. Here's the most critical transition, is that when you go to number 9, I want space in between these problems. I don't want to try and guess where number 9 begins and number 8 ends, okay? And I certainly don't want you to put the answer to number 9 up here and then the work for number 9 down here. You want to keep everything in the same section, okay? Now, so when you get to number 9, it's going to accelerate, and I've given you the distance, time. You're going to try and figure out that acceleration. Yes?
Can I just like draw a line, or do you need like space in between?
No. You don't have to draw a line. You can just leave a space. You don't have to draw a line. Some people do. Some people like to do this, and some people will draw like stars, and they'll shade it in, and they'll put like Aztec type designs in there. Okay. I just want when I look at this, I want a visual clue that says, here's where 8 ends, here's where 9 begins. Okay? Now, when you get to a situation like number 11, okay, or even on number 10, on number 10, I'm going to say, hey, sketch a velocity time graph. If you're going to do this on number 10, you can just come over here and make this velocity time graph over here. If you want to do it on an actual sheet of paper, on an actual graph paper, you can. Or you can just do it off to the side. That's up to you. Okay? But again, keep everything organized. Now, where it's going to be most critical is when you get to a situation like on number 11. Number 11 has a whole bunch of parts to it. So what I'm looking for on number 11, like it says, basically it's a softball game. Runs in 4 meters per second, slides into second base, takes her 5.5 seconds to come to rest, draw motion diagrams. So what I'm looking for on my motion diagrams on number 11 is something like this. And you don't have to be a phenomenal artist to do this. So you don't even have to draw the person. All I want you to say is okay, hey, this person sliding in with some initial velocity. 1 of 3 things can happen when she begins to slide. The velocity vectors get bigger, the velocity vectors get smaller, the velocity vectors stay the same. So in this case, what are they going to do? Smaller. She's sliding into second base. She's going to come to a stop. So just come over here and go, okay, here's V2. Draw that a little bit smaller because she's slowing down. Now, which direction are my acceleration vectors going to point? Same direction, opposite direction. Yeah, so just come in here and go, okay, she's going to have some negative acceleration. That's all you have to have for the motion diagrams. Okay? Draw me a couple of velocity vectors, and then either the acceleration vector points in the same direction or it points in the opposite direction. Okay? That's all I need. Now, when you get to B, what's your acceleration? So there's A. So then you're going to have calculate B, and again, how are you going to get that acceleration? And then have C. So you want to keep these as separate, basically sub-problems. I want C here. I don't want the answer for C up here and the work for C down here. You keep everything stacked so that I can go from an answer directly over to the work that generates that answer. Okay? That's what you want to think through. Now, let's talk about number 17. So on 17, you got a driver traveling at 20 kilometers per hour, abruptly stops the car in 3 meters. Later, while driving at 40 kilometers per hour, they stop at the same acceleration. Now, here's the deal. You've got 20 kilometers per hour, and in big bold letters on the front, just in case you needed something, I tell you all calculations must be done in the MKS system of units. So you have 20 kilometers per hour. What are you going to do with that? Yeah, 1 kilometer is, 1 hour is 3,600 seconds. Shortcut it, multiply by 10, divide by 36. Now, notice that that 20.0 has 3 significant digits in it. When you convert that into meters per second, you need to keep at least 3 digits in that conversion, okay? At least 3, maybe 4, but at a minimum of 3. Do not round your sub-calculations. Yes?
So if we put more than 6 things, you won't count us wrong.
No,
right?
actually, no.
Or you want
No,
us
no,
to
no.
do 6 things?
A minimum of 3,
So we can do more.
yes.
And won't get
Especially
counted
in that sub-calculation.
Okay, good.
Okay, but when you round to, when you get to the final answer, that's when, that's gonna be the most critical part as far as significant digits go. Okay? Now, here's
so
the
For the
deal.
final answer, you need the right amount.
Oh, we
On
do need the right amount.
17, what do you not have in problem 17? Which variable do you not have in 17? Time. So what's gonna happen on 17, you're gonna use that equation twice, okay? The first time you're gonna use it to find an acceleration, the second time you're gonna use it to find a distance, okay? So that 17 is the classic example of when you're gonna use that equation. Okay, I'm done. Good luck, you get your first real physics assignment.
See you tomorrow.